let us see that every K cell is compact. So what is a K cell? The K cell is basically a rectangular prism that is the points x1, xk such that each of these coordinates is in between some number aj and bj for every coordinate j from 1 to k. Okay, so we are talking here, as I was saying, a rectangular prism in 3D, or the higher dimensional equivalent, okay? But for simplicity, let's look into the case k equal 2. Let's do the proof just in the case k equal 2 so that we understand the ideas. The ideas are the same in every dimension anyway. So let's take A1, B1, A2, B2. Okay, and we have this here is our K cell. Okay, so in K equal 2 is just a parallelepiped. Well, actually, a parallelogram. All right, so there is an important quantity that we are going to be using, that is the diagonal. Okay, this diagonal here that we are going to call delta. Okay, so delta is the square root by the Pythagorean theorem of b1 minus a1 squared plus b2 minus a2 squared. And here the important thing about this diagonal is that whatever two numbers I pick, x and y, that are in the K cell, in the parallelogram, then I know for sure that x minus y is less or equal than delta for every x, y in I. Okay, so this we don't actually need, so we can just write the property like this. This is because the diagonal is the longest distance between 2 points inside of the K cell. Okay. In the book, you can see they define the diagonal of the rectangular prism. So it's a more complicated expression, but the idea is the same. All right. So what we are going to do, because we want to show that it's compact, let's assume for contradiction that the K cell is not compact. Not compact means that there exists an open cover G alpha, an open cover of I with no finite subcover. Okay, the opposite of this would be that for every open cover, we will be able to find a finite subcover, and then I would be compact and we would be done. So we are assuming the opposite. So what do we do? Let me do another picture of the K cell. There we go. So this is A1, this is B1, A2, and B2. What we are going to do, let me give the geometric idea. We are going to split the K cell into 4 identical pieces by taking the midpoints of the two segments A1B1 and A2B2. What is the formula for that? So the formula for that is Cj, which is the sum of Aj plus Bj divided by 2, the average. Okay, this splits my K cell into 4 smaller cells, and we are going to pick one of them because at least one of the subcells, we are going to call it I1. This I1 cannot be covered by a finite subcollection of the G alpha. Otherwise, I mean, if all 4 subcells, in general 2 to the k subcells, if all 4 could be covered by a finite subcollection of G alpha, then I could put all 4 subcollections together, and then I would be able to cover the whole thing by a finite subcollection, which I'm assuming I can't. Okay, so let's say that the one that I cannot cover, there may be more than one, but let's say there is one, is the top left, sorry, the top right, and that one is my I1. Okay, it doesn't matter very much which one it is. The important thing here is that there is one. And now what do we do? What we are going to do, we are going to take the cell I1 that I just found, and I'm going to subdivide it. Oops, I'm going to subdivide it into 4 subcells. Okay, and that way I will find I2 as one subcell that cannot be covered by a finite subcollection. And I can iterate this process. Okay, and I will find a sequence I1, I2, I3, and so on of nested subcells. It's bigger than the next. Okay, they are getting smaller and smaller and smaller. And they have 3 properties. The first one is that it's a nested sequence. The second one is that none of these can be covered by any finite subcollection of G alpha. And the third property is that if I have 2 points X and Y in IN, then X minus Y is lesser or equal than delta divided by 2n. Why is this? Because I'm subdividing, I'm dividing by 2 every time, the lengths of the sides, and I'm dividing n times. Okay, so actually I'm dividing the side by 2, and then that implies that the diagonal also must be divided by 2 to the n. Okay, it's a Pythagorean theorem applied n times. All right, so now there is something here that we need to observe, that is that if n is very large, this number is very small. Regardless of the original delta, this will get smaller as n gets large, and n can get as large as we want. So now let me tell you, the idea here is that when I take the intersection of all these subcells, IN, the intersection is not empty. So what happens then? This means that there exists some X star that belongs to every IN, because intersection is non-empty. Okay, if this X star didn't exist, then the intersection would be empty. And now, because this X star is a point in the original cell, it's a point that is covered by the collection G alpha. So in particular, X star is covered by some G alpha open. And now let me show you what is the idea with a picture. So we have here our G alpha. And we have here our X star. And because G alpha is open, there exists some neighborhood of X star, okay? That is a ball, because we are in 2D, that is completely contained in G alpha. This is because G alpha is open. But now, because all the cells contain our X star, some of the cells may or may not be inside this G alpha or this ball. But the truth is, as I keep subdividing, what is going to happen? I'm going to reach some critical size. And from there on, the cells are always going to be contained in my ball BR X star. Okay, you see that what is happening here? What is happening here is that IN is going to be contained in BRX star for n large enough. Okay, remember I'm subdividing and subdividing and subdividing. So at some point I'm operating really, really close to X star, to the point that there is no way to distinguish from a certain distance the subcell from the point itself. Okay, so it will for sure be inside this ball I'm saying, and definitely inside of the G alpha. Okay. If you don't completely trust this I'm saying, well, we can always say, well, what is the distance between X star and Y for any Y in the IN? So this is delta divided by 2n. This is by property 3, and this is true for every Y in IN. Okay, but I know that delta divided by 2n is less than R. Okay, for n large enough. We just need to keep dividing and dividing and dividing. And this is true because R is Archimedean. So what is our conclusion here? Our conclusion is that IN can be covered by G alpha. So we are not saying if this is like the best. It's not that it's covered by a collection, it's just covered by one of the G alphas. And this is a contradiction with 2. Okay, we go back to say that IN was not covered by any finite subcollection of the G alpha. Here we are saying that there is one G alpha that covers, that cannot be, so we are done.